Welcome back, and this is another daily LeetCode problem. So today it was called maximum width of a binary tree. And so yeah, it's yet again another tree question where it's not a balanced binary tree or like a complete, so it only can have at most, each node can have only at most 2 children. But you can see here, like there could be null nodes at any point in the tree, and these values themselves aren't actually sorted. So it's not like a search tree or anything. So yeah, so what you want to do is find the maximum width. And it's interesting how they did it for this. Like, although one could argue that, okay, this looks like the width is like, maybe say 1, 2, 3, 4, 5, 6. You get 7 here because if you counted like the bottom layer here from left to right and pretend like there would be nodes here where they're actually null, you would get 7. So it's like 1, 2, this would go down, 3, 4, then once again there's another one, this is 5, 6, and then this is the 7th here. Okay, and so you have to kind of fill in the bottom width here and pretend like what is actually null are actually nodes, and that's how you get this width. But what matters a lot here is you'll see in this example is that you can't include, like, say if you fill this out again, you can't actually say that there's a width of 4 because you want it to end at, that width ends like at the beginning, or you have to have at least a node here. Like if there was a node here and not one here, you would actually get a width of 8. So you're actually constrained by whichever one, by reading from left to right here, and there has to be some node in order to reach it. And so although all these are empty, as long as there's some node on this side, you can count them all. If that makes, I hope that makes sense. But for this one, you can see because it ends at the very beginning here, that would only give you a width of 1 because you can't count all these missing nodes here. But if there was one here, then you could count all 4 of them. But because the one is here, you're constrained to this one, and so you would only count 1 instead of like all 4 of these if this one existed. Okay, and so instead, you just want to grab these 2 here. So, and that's how you get the output of 1. All right, and so that's kind of the definition of what they would call the maximum width. Now for the algorithm for this, it was pretty intuitive to come up with like a breadth first search solution, because often I like the name called like level order traversal. So you kind of want to explore this frontier level by level. And then as you're exploring each level, you just count kind of the maximum width of each nodes as you visit each level. And then you just, each time you compute what the maximum width is for that, or what the width is for that level, you just take the maximum. Okay, so I'll do this iteratively just because I find for BFS, for trees, typically doing an iterative solution is the simplest. So let's go ahead and make our queue. So I like to call it just queue. And let's import up here. So from our collections, let's import dq, or double into queue. And so here we just want to pass in the root inside of that queue, and we want to keep iterating while there's something inside of our queue. And we're going to want to return our response here, and this will represent like the maximum width, so res. Why don't we actually call it max width to make it simpler, but typically I like calling it res. And so initially, why don't we just set this max width to 0? Just move my keyboard there. Okay, and so this is kind of just blueprint code for like these breadth first search like iterative traversals. So all this is just kind of templated code that you just memorize. And so you just say, okay, for underscore in the range. So we want to iterate through every single thing in our queue. And then we just want to say, okay, the current node is whatever we just pop off of our queue. Okay, and so that's good. And then what we want to do is then we just want to add to our queue. If there's something on the left, of this current node, then why don't we add that to our queue? So it's queue.append node.left, and we can just put that here. And then we'll just repeat this, but for the right side. Perfect. All right, and so now the main question is, okay, how do we actually maintain these levels here? Because right now we're just adding each node to our queue, and then we'll pop it off. So right now we're exploring each level, and say if we printed this out here, we could do like print, oh no, print, like that. Is we'll print this node. If we run that, you'll see that we're properly, oh, I'll do node.val. There we go. So you can see for this tree, like we're doing a breadth first search right now. We're doing 1, 3, 2, 5, 3, 9, like you should be. But now we want to do, okay, how do we actually get the levels here? And so what we want to do is we want to say, okay, why don't we actually append the level as well? So initially the level is 0. And so when we pop this off our tree, we're also going to get like the current level that you're on. We'll just call this I. And so then what you can do is not only the level, but why don't we get the actual location of every node? So this is node 0, 1, 2, 2, 3, 4, and then 5 doesn't exist, but then we'll have 6 here. And so what we can do is, in order to get this width of 4, we can just get the maximum node on the right minus the node on the left plus 1. And so that will give us 4. Okay, so like max right minus the max or the node on the left, and then plus 1, right? And so that would be 6 minus 3 plus 1, and that'll get you 4. So why don't we, and so in order to get these actual node numbers, like I did 1, 2, 3, or 0, 1, 2, 3, 4, 6, is at every iteration, we want to add this index when we're appending to our queue, but then we want to take I and times it by 2. And then for the right node, we want to do the exact same thing, but we want to do I times 2 plus 1, because it's always an extra node over. And so this times 2 comes from, okay, since this goes 0, 1, 2, then this node here will actually end up being 4, because it goes, or 0, 1, 2, 3, 4. What's going on here? No dot left. I think this should work. Why don't we print these? I'm going crazy for a second. Print I. Let's just do this, and then get that node value, just so we can kind of see the behavior of this. Oh, q.pop left. And we want to make this a tuple. There we go. So we want to undo this because we want to keep it in an array, but then we want to put a tuple inside of the array. Great. Okay, so then we have, what do we have here? 0, 0, 1. That doesn't look right. Why don't we set this at 1 initially? So 1, 2, 3, 4, 5. Okay, so I just had the math wrong. So you want to start with a node value of 1 here. So it goes 1, 2, 3, 4, then 5. And so then whenever you do, say, this node you hear, then the node to the left would be times 2, which is 6. And then the node to the right will be times 2. So 3 times 2 is 6, plus 1 is 7, right? And so for this node, the way you get the indexes for these, or the node numbers, is you just do 2 times 2 for the left one, which is 4, and 2 times 2 plus 1, which is 5, right? And so the math works out that way. Okay, so sorry about the confusion there. And so other than that, the only thing that we have to do is be updating this max width. And that we can actually do just right here, where we say the max width is equal to the maximum of the current max width, because we want to compare the current running max width. And then we do our formula there, which is, okay, why don't we take our queue and get the thing that's at the end of the queue, which if we're looking at this level, these would be the values on, these would be the 3 nodes on our queue. And we want to get the node to the right of it, on the rightmost node, which is -1 here. And then we want to get indexed into 1 value, which is then the number of that particular node, which is like I here. And then let's minus it by the first node in our queue, which would be this node. And we want to get its like index value. And then just +1, right? And so that's how we get, I believe this number is, so 1, 2, 3, 6. So this is node 7. And then this is node 4. And so then we'll do 7 minus 4 plus 1. And that's how we'll get that width of 4 that we want. Okay, and so let's run that. And success. And let's go ahead and submit it. And so yeah, that's today's daily LeetCode problem. So I think it's fairly intuitive. I think the main catch here is just that you have to understand the node ordering, or like the math behind it. So knowing like, okay, to get the node number of the left and right children, it's I times 2 and I times 2 plus 1. And then the only other trick that kind of also makes this a medium level question is just knowing how to get the max width, which is just comparing the rightmost node's index value and the leftmost node's index value and just adding 1 to it. Okay, so yeah, I hope that helped, and good luck with the rest of your algorithms. Thanks for watching.